Hey, welcome back. We're looking at thermal equilibrium, and I just thought it would be helpful to do another problem. So what's the idea with thermal equilibrium? Well, the idea is that if you have two objects, one hot, right, and one cold, the heat energy will always flow in this direction. The hot object will always make the cold object hotter. It won't flow back this way, although theoretically it's possible, and it may happen a little bit, but certainly we've never put a hot thing with a cold thing and seen the hot thing get hotter. It always ends up flowing from the hot one to the cold one until they end up being equal. So here's a scenario right here. Let's say you heat up a glass in a fire. Maybe you're boiling water in there or whatever, or sterilizing it. I don't know. So you heat it up. It's in the fire. It's 145 degrees Celsius you've got it up to. So you want to cool it off. So we're going to plunge it into this bucket of water right here. Okay, so how do we set this problem up? Well, here's the equation for thermal equilibrium. We've got the Q of the one thing plus the Q of the other thing equals 0. So they're going to cancel each other out. And so what are our two things? Well, we have this piece of glass right here. So we're going to call that A. Right? And then we have this water right here, and so we're going to call that B. And so we have the mass of the water. So to solve for Q, Q is going to be your heat transfer. So you have the mass of the water times the specific heat, mass of the glass times the specific heat of the glass times the temperature change of the glass, plus the temperature change of the water times its specific heat times its mass. So these are going to flow into each other. Now let's go ahead and set this up. And I just went ahead and put all these things in here prior just to make it a little bit faster. But here's my mass right here. And here's my specific heat of glass. You can just look that up. So that's 840 joules per kilogram degree Celsius. And my final temperature is what we're looking for here. So I guess I didn't sort of illustrate that. So what I want is, what is my temperature of my water after I plunge my hot piece of glass in there? Okay. So I know that my original temperature of the glass was 145 degrees, and the final temperature is going to be much lower, because once again, the hot one's going to get colder and the colder one's going to get hotter. So this is going to be a smaller number to this, so this side's going to end up being negative. And then I'm going to add to this side, it's going to end up being positive, you see. But the two of them together, of course, will cancel out and equal 0. Because there's no new energy being added. You just have energy being transferred from this to this. So if you know the energy in this and you know some things about this, you can figure out what the final temperature will be. So here's my final temperature. It's going to be the same for both of them because they end up in the same thing. They become, the two objects become one system. All right, so we go ahead and we put this in here, and this is 5 liters of water. Now the nice thing about water is that 1 liter of water equals 1 kilogram. That's just for water. For the other things, you're going to have to know the density in order to figure that one out. But for water, it's pretty simple. And so we know that's 5 kilograms of water is going to be my mass there. My specific heat of liquid water is 4,180 joules per kilogram degrees Celsius. And I have my final temperature minus my initial temperature of my water. All right, so go ahead and distribute these things out, and I'm going to go ahead and combine my TFs right here. I'm going to pull my other number over to the side. I'm going to divide by that, just a little bit of algebra right here, and I'm going to end up with my final temperature is 21.5 degrees. So even though this was quite hot, it really didn't raise the overall temperature of this water very much. And why? Well, mostly because water is such a great heat absorber. It has this enormous specific heat, which actually comes because the bonds, the hydrogen bonds in water flex. And so when that energy goes in there, those bonds flex and absorb the energy, kind of like a shock absorber. So it takes an enormous amount of energy to get these things moving real fast. But yeah, that's the situation. Oftentimes you'll be given one of these thermal equilibrium problems and be asked for final temperature. It's a quick little simple example problem. Hopefully that helps you.